Welcome to this comprehensive course on Service Mesh, a critical component in modern microservices architectures. In today's rapidly evolving technology landscape, service meshes have become increasingly important as organizations move towards microservices architectures. Throughout this session, we'll explore how service meshes solve complex challenges in service-to-service communication and how they can be effectively implemented in your own projects. Whether you're a DevOps engineer, system architect, or developer working with distributed systems, this course will equip you with the knowledge and practical skills needed to work with service meshes effectively. We'll cover everything from basic concepts to advanced implementations, with plenty of hands-on examples using popular tools like Linkerd and Istio. Let's begin this exciting journey into the world of service meshes together. Let's start by understanding what a service mesh is and why it has become such a crucial part of modern infrastructure. A service mesh is fundamentally a dedicated infrastructure layer that handles service-to-service communication in your microservices architecture. Think of it as a specialized network that sits between your services, managing and controlling how they talk to each other. This might sound simple, but its implications are profound. In traditional monolithic applications, service communication was straightforward. Everything happened within the same application. However, in a microservices world, we're dealing with hundreds or even thousands of services that need to communicate reliably and securely. The purpose of a service mesh extends far beyond simple communication. It enhances four critical aspects of your architecture: observability, reliability, security, and control. Let's break these down. Observability means you can see exactly what's happening between your services, which services are talking to each other, how long requests are taking, and where bottlenecks might be occurring. This is like having X-ray vision into your application's communication patterns. Reliability features ensure your services can handle failures gracefully. The service mesh can automatically retry failed requests, implement circuit breakers to prevent cascade failures, and balance load across multiple instances of a service. Security is enhanced through automatic encryption of all service-to-service communication, along with identity-based authentication and authorization. This means you don't have to implement these security features in your application code. Control allows you to implement sophisticated traffic management patterns like A/B testing, canary deployments, and fault injection for testing, all without modifying your application code. As we progress through this course, you'll see how these capabilities translate into practical benefits for your applications and your development teams. The service mesh architecture consists of two primary components: the data plane and the control plane. Understanding these components is crucial for grasping how a service mesh operates. Let's start with the data plane. The data plane consists of a network of lightweight network proxies that are deployed alongside your service instances as what we call sidecars. Popular proxy implementations include Envoy and Linkerd. These proxies intercept all network traffic going to and from your services. Think of these proxies as smart assistants that sit next to each of your services. When Service A wants to talk to Service B, the communication doesn't happen directly. Instead, it goes through these proxy sidecars, which can perform various operations like load balancing, circuit breaking, or collecting metrics, all transparent to your application. The control plane, on the other hand, is the brain of the operation. It manages and configures all these proxies, controls traffic behavior, and enforces policies across your entire mesh. It's where you define rules like route 10% of traffic to the new version, or ensure all service-to-service communication is encrypted. A key advantage of this architecture is the separation of concerns. Your application code focuses on business logic, while the service mesh handles all the complex networking and operational concerns. This separation makes your applications easier to develop, test, and maintain. In practice, when you're troubleshooting issues or implementing new features, you'll interact primarily with the control plane's APIs and tools, while the data plane quietly does its job in the background. Let's delve into the powerful features that make service meshes so valuable in modern architectures. These features form the backbone of what makes service meshes indispensable in complex microservices deployments. First, let's discuss traffic management. This isn't just simple load balancing, it's a sophisticated system for controlling how requests flow through your application. You can implement advanced patterns like circuit breaking, which prevents cascade failures by stopping traffic to failing services. You can perform traffic shifting, allowing you to gradually route traffic from an old version of a service to a new one, enabling safe deployments. The load balancing capabilities go beyond round-robin distribution, offering options like least connected or latency-based routing. Security in a service mesh is comprehensive and automated. The mesh automatically establishes mutual TLS, MTLS, encryption between services, ensuring all communication is secure by default. This is particularly important in zero-trust environments. Access control and authorization policies can be defined at a granular level, allowing you to specify exactly which services can communicate with each other and under what conditions. The observability features are particularly powerful. The mesh collects detailed metrics about every request, latency, error rates, throughput, and more. This data is aggregated and can be visualized through dashboards, giving you real-time insight into your system's behavior. The tracing capability provides end-to-end visibility into request flows, helping you understand how requests propagate through your system and identify bottlenecks. Logging is centralized and enriched with metadata about the services involved, making it easier to debug issues and understand system behavior. The mesh can automatically correlate logs across services, giving you a complete picture of each request's journey through your system. These features work together to provide a robust platform for running microservices at scale. As we progress through the course, you'll learn how to leverage each of these features effectively in your own deployments. The benefits of implementing a service mesh extend far beyond just technical capabilities. Let's explore how these benefits translate into real-world advantages for your organization. Reliability is perhaps the most immediate benefit. The service mesh provides built-in resilience patterns like circuit breaking and retries. When a service starts failing, the circuit breaker kicks in to prevent cascade failures that could bring down your entire application. The retry mechanism automatically handles transient failures, improving the overall reliability of your system. Timeout and rate-limiting features protect your services from being overwhelmed. You can set specific timeout values for different types of requests and limit the rate at which services can be called. This prevents slow services from backing up the entire system and protects against potential denial of service situations. The ease of deployment is a game changer for DevOps teams. Instead of implementing complex communication patterns in each service, these patterns are managed centrally through the service mesh. This means you can update communication policies, security rules, or monitoring configurations without touching any application code. This centralized management significantly reduces the operational burden on development teams. They can focus on business logic while the service mesh handles the complex networking and operational concerns. When you need to implement a new security policy or change how services communicate, you can do it through the service mesh's control plane rather than updating dozens or hundreds of services individually. These benefits become particularly apparent as your microservices architecture grows. The service mesh scales with your application, providing consistent behavior and management capabilities regardless of how many services you're running. Before implementing a service mesh, it's important to understand the trade-offs and considerations involved. Let's examine these factors carefully to help you make informed decisions in your own implementations. The first consideration is overhead. Every request in your system now goes through two proxy instances, one on the sending side and one on the receiving side. This introduces additional latency to each request. While modern service mesh implementations are highly optimized, you might see latency increases of a few milliseconds per request. In most cases, the benefits outweigh this cost, but it's important to benchmark your specific use case. Complexity is another significant consideration. While a service mesh simplifies many operational aspects, it also introduces another layer of infrastructure that needs to be managed and maintained. Your team will need to understand how to configure and troubleshoot the service mesh itself. This learning curve can be steep, especially for teams new to the technology. When choosing a service mesh, several factors need to be considered. Community support is crucial. A strong community means better documentation, more tools, and faster bug fixes. The feature set should match your requirements. Some service meshes are more lightweight while others offer more advanced features. Integration capabilities with your existing infrastructure are also important. Consider how well the service mesh works with your current tooling and deployment platforms. Memory and CPU overhead should also be considered. Each sidecar proxy consumes resources, and in a large deployment, this can add up to significant resource usage. Proper capacity planning is essential to ensure your infrastructure can handle the additional load. These considerations shouldn't discourage you from implementing a service mesh, but they should inform your approach and help you plan for a successful deployment. Let's explore the major service mesh implementations available today, each with its own strengths and use cases. Linkerd, often considered the pioneer in the service mesh space, is known for its simplicity and ease of use. It's particularly well suited for Kubernetes environments and focuses on providing essential features without unnecessary complexity. Linkerd is written in Rust, which gives it excellent performance characteristics. Its simplicity makes it an excellent choice for teams just starting with service mesh technology. Istio, backed by Google, is arguably the most feature-rich service mesh available. It's built on top of the Envoy proxy and offers sophisticated traffic management capabilities, strong security features, and comprehensive observability tools. While it has a steeper learning curve, it provides the flexibility and features needed for complex enterprise deployments. Consul Connect, part of HashiCorp's Consul, takes a unique approach by integrating service mesh capabilities with service discovery. It's particularly strong in hybrid and multi-data center scenarios, making it a good choice for organizations with complex infrastructure spanning multiple environments. AWS App Mesh is Amazon's managed service mesh offering. It's deeply integrated with other AWS services, making it an attractive choice for organizations heavily invested in the AWS ecosystem. It provides seamless integration with services like AWS X-Ray for tracing and Amazon CloudWatch for monitoring. Envoy, while technically a proxy rather than a complete service mesh, deserves mention as it forms the foundation for many service mesh implementations. Created by Lyft, it's known for its high performance, extensive feature set, and robust API. Many organizations build custom service mesh solutions using Envoy as the data plane. As we progress through this course, we'll focus primarily on Linkerd for our hands-on examples, as it provides an excellent balance of features and simplicity for learning purposes. Now we're transitioning into the practical portion of our course, where we'll focus on Linkerd, one of the most popular and user-friendly service mesh implementations available. Linkerd is an excellent choice for our hands-on exercises for several reasons. First, it's open source and has a thriving community, which means you'll have access to extensive documentation and support resources. Second, it's designed with simplicity in mind, making it ideal for learning the core concepts of service mesh technology. Finally, it's production-ready and used by many organizations in their critical infrastructure. In the upcoming sections, we'll walk through the installation process, deploy sample applications, and learn how to leverage Linkerd's features for traffic management, observability, and security. By the end of this section, you'll have practical experience with implementing and managing a service mesh in a real-world scenario. Let's begin with the installation process and gradually build up to more complex configurations and use cases. Let's walk through the process of installing Linkerd in your Kubernetes cluster. The installation process is straightforward, but there are some important details to understand. First, we'll install the Linkerd CLI tool. The command curl cell https://run.linkerd.io/ installs downloads and installs the latest version of the Linkerd command line interface. This tool will be your primary means of interacting with Linkerd. After installation, you need to add Linkerd to your path environment variable with the command export path equals $path: home/.linkerd2/bin. This ensures that you can run Linkerd commands from any directory. For permanent access, you might want to add this line to your shell's configuration file, .bashrc, cshrc, etc. The final step is to install Linkerd on your Kubernetes cluster, using linkerd install kubectl apply -f. This command generates the necessary Kubernetes manifests and applies them to your cluster. The installation includes the control plane components and CRDs, custom resource definitions, that Linkerd needs to function. Before proceeding with the installation, ensure that your Kubernetes cluster meets Linkerd's requirements. The cluster should be running Kubernetes version 1.2.1 or later, and you should have cluster admin privileges. After installation, it's crucial to verify that everything is working correctly. We'll cover these verification steps in our next slides. Now that we have Linkerd installed, let's deploy our first application to demonstrate service mesh capabilities. We'll start with a PostgreSQL database deployment, which will serve as the backend for our application. The deployment consists of two Kubernetes resources, a service and a deployment. The service creates a stable network endpoint for accessing the database, while the deployment manages the PostgreSQL pod. Let's examine the key components of this configuration. In the service definition, we're creating a service named Postgres that exposes port 5432, the default PostgreSQL port. The selector app, Postgres, ensures that the service routes traffic to pods with the matching label. In the deployment configuration, we're setting up a single replica of PostgreSQL. The container configuration includes important environment variables, Postgres_DB, Postgres_user, and Postgres_password. In a production environment, you would want to manage these credentials more securely using Kubernetes secrets. To deploy this configuration, save it to a file named postgres.yaml and apply it with kubectl apply -f postgres.yaml. After deployment, Kubernetes will create the necessary resources and start the PostgreSQL container. This database will form the foundation for our microservices example, which we'll continue building in the next slide. Remember to monitor the deployment status using kubectl get pods to ensure everything starts correctly. Let's continue building our application by deploying the web application component that will interact with our PostgreSQL database. This example demonstrates a typical microservices architecture that we'll enhance with service mesh capabilities. The configuration we're looking at defines two Kubernetes resources, a service and a deployment for our web application. The service creates a network endpoint on port 80 and forwards traffic to port 8080 on our application pods. This port mapping is a common pattern in web applications. In the deployment configuration, we're setting up a single replica of our web application. The container specification uses a placeholder image, your web app image, tag in a real deployment. You would replace this with your actual application image. The container port specification of 8080 matches the target port in our service definition. A few important points to note about this configuration. First, we're using the label app, web app consistently across both the service selector and the pod template. This label matching is crucial for service discovery. Second, we've kept the configuration minimal for learning purposes, but in a production environment, you'd want to add resource limits, health checks, and possibly configuration maps or secrets. This deployment will form the basis for demonstrating Linkerd's features, including traffic management, observability, and security patterns. After deploying this configuration with kubectl, apply -fweb app.yaml, we'll be ready to inject the Linkerd sidecar proxies and enable service mesh functionality. Now that we have our application components deployed, let's integrate them with Linkerd to enable service mesh capabilities. This process involves several steps that we'll walk through carefully. First, we need to verify that Linkerd is running correctly in our cluster using Linkerd check. This command performs a series of checks to ensure that the control plane is healthy and ready to handle our workload. It's a crucial step before proceeding with mesh integration. The key step is injecting Linkerd's proxy into our deployments. The command kubectl get deploy -o Linkerd inject -kubectl apply -f might look complex, but let's break it down. Kubectl get deploy -o JSON retrieves our deployments in JSON format. Linkerd inject adds the proxy configuration to each deployment. The final kubectl apply applies the modified configurations. After injection, verify the proxy status with Linkerd -n namespace check -minus proxy. This ensures that the proxies are running correctly in your deployments. To access your web service, use kubectl get svc web app to get the external IP. For monitoring, you can access the Linkerd dashboard by port forwarding with kubectl -n Linkerd port forward svc/Linkerd web 8084 to 8084 and navigating to http://localhost:8084. The dashboard provides valuable insights into your service mesh, including traffic patterns, success rates, and latency metrics. Take some time to explore these features. They'll be invaluable for monitoring and troubleshooting your application. For your final assignment in this course, you'll put your service mesh knowledge into practice by deploying a pod with two containers that communicate with each other, then managing that communication using Linkerd. This assignment is designed to reinforce several key concepts we've covered. Container deployment and configuration in Kubernetes. Inter-container communication patterns. Service mesh integration and management. Observability and monitoring. Here's what you'll learn from this assignment. How to design and implement inter-container communication. How to properly inject and configure Linkerd sidecars. How to monitor and analyze container-to-container traffic. How to apply service mesh patterns in a practical scenario. This knowledge will be valuable in real-world scenarios where you need to design microservices architectures, implement secure service-to-service communication, monitor and troubleshoot distributed applications, scale and manage complex applications. Remember to leverage the Linkerd dashboard for monitoring your deployment, and don't hesitate to experiment with different configuration options. This hands-on experience will be invaluable in your DevOps career. We've now reached the end of this module on service mesh technology. As we wrap up, I encourage you to reflect on what we've covered and how it fits into your broader understanding of DevOps practices. This is a good time to review any concepts that might need clarification. Remember that service mesh technology is constantly evolving, and staying current with the latest developments will be important in your DevOps journey. Congratulations! You've now completed not just this module on service mesh, but the entire DevOps course. This journey has taken us through various crucial aspects of modern software development and operations, culminating in this advanced discussion of service mesh technology. Throughout this session, we've covered fundamental DevOps principles, continuous integration and delivery, containerization, orchestration, monitoring, and now service mesh implementation. Each of these topics builds upon the others to create a comprehensive understanding of modern DevOps practices. The skills you've acquired in this course are highly valuable in today's technology landscape. From basic scripting to advanced service mesh configuration, you now have the tools to design and implement robust CI/CD pipelines, manage containerized applications at scale, implement secure and observable microservices, architectures, make informed decisions about infrastructure and tooling. Remember that DevOps is a journey of continuous learning. The field evolves rapidly, and the principles and practices we've discussed will serve as a foundation for your ongoing professional development. I want to thank you for your participation and dedication throughout this session. Your engagement and questions have made this an enriching experience for everyone involved. I wish you the best in your DevOps career and encourage you to stay curious and keep learning. Please stay in touch through professional networks, and don't hesitate to share your successes and challenges as you apply these concepts in your work.